So in other words, you can state this theorem as every continuous function is Riemann integrable. So let's start. Now since f is continuous on closed interval AB, this implies f is uniformly continuous. This is a result. So it is uniformly continuous on closed interval AB. Then for given epsilon positive, there exists delta positive depending upon epsilon only. This is a definition for the uniformly continuous. For uniformly continuous, this delta positive depends only upon epsilon, right? So because f is uniformly continuous on closed interval AB, let's use the definition for this, that then for given positive epsilon, there exists delta positive depending on epsilon only, such that difference of x minus y mod is less than delta, implies, yes, mod of f of x minus f of y, this mode is less than epsilon for all xy belonging to this closed interval AB. Just mark this as 1. This is just the definition for this uniformly continuous function. Now choose a partition P of closed interval AB such that delta xi is less than this delta. Now this delta and this delta denoted as the same name as delta only. So please just concentrate on this, that this is delta xi and this is also delta for all I equal to 1 to up to n. Okay. Now let's define capital Mi and small mi. Capital Mi is equal to supremum of f of x over close interval xi minus 1 xi, and this small mi, this is the infimum of fx over this close interval xi minus 1 xi. Very fine. Okay. Now since f is continuous on closed interval AB, and hence because it is continuous on this interval, of course then it is also continuous on this closed interval xi minus 1 xi, which all just a segment which is belonging to this closed interval bigger 1. So therefore f attains its maximum and minimum values on this closed interval. Just look at the interval in the figure. This is xi minus 1 xi, and this is your small mi, which is the infimum of fx over this bigger interval, and this is the supremum of fx over this bigger interval. Now because f is continuous on this interval, so their supremum need not be the maximum value, right? So I will be taking, okay, let me first give you the example for this. If function is continuous on closed interval AB, it attains its minimum and maximum value on this. Supremum need not be maximum. For example, if I am having the function sin x, and if I am having the open interval 0 to pi by 2, I know that supremum of sin of x is what? The range is minus 1 and 1. So supremum is 1, right? Okay. Now here, because f attains its maximum minimum values, there exists the point si ti in this closed interval. Let me say that it attains the maximum value at si and minimum value at this ti. Let's suppose that. Okay. Let's suppose that f attains its maximum value at this point. Now, after this, okay, let me mention there only. There exist these points such that this capital Mi is equal to f of Si, because diagram is here, so I'm writing here, and small mi is equal to f of ti. Alright. In this proof, I have taken ti first. It's my choice, it's your choice. Whatever point you want to take, you want to choose. You can write si over here or ti over there. It's your choice, okay? Alright, next is, now since si and ti belongs to xi minus 1 xi, so therefore the modulus of si minus ti, this modulus is less than equal to, yes, difference of this. Likewise we have done in the previous theorem where I'm having here capital Mi and small mi, right? I have taken their difference, which is always positive, so there is no need of mode, and this is a result. Alright, whenever 2 points belongs to the closed interval, their difference is always less than equal to the difference at the end points. So distance between the middle points always less than the distance between the extreme points. And here extreme points are xi and xi minus 1. And these are the middle points. So their difference is less than equal to this difference. This is nothing but delta xi. And this is, we have taken this to be less than this delta. Okay, so this implies mod of si minus ti is less than delta. Please don't confuse with this. I have written si like this and here it is si. It is one and the same thing. Don't confuse up. So this implies, now whenever si minus ti mod less than delta, if we take the value of the function at these points, their difference, then that will be f of si. Okay, again I have written s like this. Please excuse me. So this is f of ti. This mode is less than epsilon according to the definition of the uniformly continuous function. Okay, that is from 1. Look here, I have marked this as 1. Whenever these 2 points is less than delta, then the value of f at these 2 points, their difference is less than epsilon. Now because we have got this difference to be less than delta, so the value of f at these points with their difference is less than epsilon, using 1 or from 1. Very fine. So this implies, this is what f of si, we have taken this to be capital Mi, because function is continuous all over the interval, so it attains its maximum and minimum values. Suppose at si and ti, from there I have taken this f of si to be equal to capital Mi and f of ti to be small mi. This mode is less than epsilon, which implies, because it is already a positive value, so it is small, the difference is less than epsilon. You can mention over here that as capital Mi is greater than equal to small mi. Now because we have to prove that f is Riemann integrable, right? So for that, let's take UPF alpha minus LPF alpha. Let's find out this. This is equal to, now this is what, summation of, yes, I going from 1 to 1, yes, summation of, very good, capital Mi delta alpha I minus this is summation I going from 1 to n, this is small mi delta alpha I. Summation I going from 1 to n, this is capital Mi minus small mi taking this delta alpha I common. Now further, this is less than epsilon. Because it is less than epsilon, so I will write this to be, it is less than First I am writing the summation, and here it is epsilon instead of their difference. So this is equal to taking epsilon outside and summation of delta alpha I going from 1 to n delta alpha I. This is epsilon. Okay, this summation is all will be cancelled out. At the end we will be lefting up with value of alpha at b minus value of alpha at a, right? And say this is equal to, this is just a number, let's say this is epsilon dash. So thus UPF alpha minus LPF alpha is strictly less than this epsilon dash, but epsilon dash was arbitrary, we have chosen. So but epsilon dash was arbitrary, so therefore whenever this thing is less than epsilon, our function is Riemann integral. This is if and only if case. We have proved this result both the ways. You can check in the previous videos. This is a result. So therefore f is Riemann integral. Let me make a beautiful R. Thank you so much. Okay, so this is Riemann integrable on closed interval AB. Here ends up our proof. Thank you so much. Just revise all the steps and just remember all the results. This is very easier way to prove. Just you have to know about the definitions and the results.